All right, everyone. Welcome. This is the video for lesson 15 from our polynomial unit. This one will be the last lesson in this subunit before we break and move on to our next big topic. But for now, we're going to study something called the remainder theorem. This is an add-on to what we did with long division. In lessons 13 and 14, we looked at the concept of polynomial long division and addressing whether something is or is not a factor of a polynomial. Um, like say x minus 2 is a factor of, x to the third minus 3x squared plus 8x minus 11, like something like that. We looked at situations like that, but one of the things that you might have realized in dealing with those polynomials is the examples that we used and the problems that we did all worked. We started with a factor or a known factor. We factored it out using polynomial long division, and we could then take the leftover piece, factor it farther, and we could verify always that, like if I said, hey, here's a factor, use long division, verify it's a factor, and it worked, and we would get a remainder of 0. Everyone was happy, and that's all great. So for every problem that we did, the division worked. But clearly, the world doesn't divide evenly. Not everything in life is evenly divisible. I mean, just think about how many times you had to put, like you have a, here's a good example that I deal with every so often. I have a carton of eggs. A carton of eggs is 12. A carton of eggs is a dozen, so it's got 12 spots. And I want to find a good way to evenly distribute 7 eggs. That's hard to do, right? And it's always going to look lopsided. Or if I've got 3 eggs or some other odd number, um, you know, because 7 doesn't divide evenly into 12, you know, trying to figure out how to get all that in there just isn't going to work. Or let's say you've got, I don't know, you've got 3 people in the house, but there's 22 cookies. Somebody's going to get 8 cookies. So you're dealing with remainders and division that doesn't work all the time. So it's useful if we had some definitions to deal with it. And so some of the definitions here, there's a big concept that we're going to look at here. And for a polynomial p of x and a number a, then the remainder on the division of x minus a is p of a. Now, that might not make a whole lot of sense at first. What that's essentially saying is that the result of the division by x minus a is going to be p of a. Now, the rest of this here is something, actually, this part you kind of already know based on our work from the last one. If a polynomial, if x minus a is a factor of the polynomial, then you get a remainder of 0. That's what the second part says. And that part we already know, right? Like if I have, say, x minus 3, okay, and I want to divide that into, say, x squared plus 4x minus 21. Let's say, and this will be a quick division, right? Now, we do know that this expression, okay, actually factors into x minus 3 times x plus 7. So I already know that that's a factor of this expression. But just to prove it, I can go ahead and do the division, right? X squared divided by x is x, and I get x squared minus 3x, subtract, change the sign, add it, 7x minus 21, and now I have x plus 7, 7x minus 21, change the signs, add 0. Okay, and that works because x minus 3 is a factor of this polynomial here, and so we get a remainder of 0. But What this now says is one step beyond this and kind of goes back to what we did in much previous units, and that this also means that the intercept of this, well, what does intercept belongs to this, right? This has an intercept at x equals 3. Why? Because it will cross the x-axis at 3. So what that means is that we also know that because it has an intercept of 3, that f of 3 will equal 0. If I plug 3 into this function, it will give me an answer of 0. And it does. 9 plus 12 is 21, minus 21 is 0. So that does work. And this, we know that it has an x-intercept of 3. We know that that means we evaluate it and it's 0. We know that it's a factor. This puts it all together and says that because x minus 3 is a factor of x squared plus 4x minus 21, we get a remainder of 0 when we divide, and f of 3 is equal to 0. Now what the remainder theorem does is it expands upon that into the general case. And you'll see that in a little bit. Okay, so let's now go on to an example of how we could use this. All right. Consider the polynomial function x to the fourth minus ux to the third plus 24x squared minus 32x plus 16. U is an unknown real number. Huh, sounds like a U problem. Okay, I had to make that pun, I'm sorry. But anyway, can we find the value of U? Well, we know from Algebra 1 that in order to solve an equation for a variable, to find the value of a variable, it has to be the only variable in the problem, which means we'd have to know the value of x. We also have to know the value of f of x. Well, let's see. We get that from this fact here. X minus 2 is a factor. If x minus 2 is a factor, then what that means is that 2 is an intercept. In other words, it's going to cross the x-axis at 2, and we also know that f of 2 is equal to 0. That gives us the values to plug into this function, because now that's telling us that if x is 2, then the output, the f of x, is equal to 0. And so now what I have is I have 0 equals, oops, having a hard time writing here. Let's back that up a bit. 0 equals 2 to the fourth minus u times 2 to the third plus 24 times 2 squared minus 32 times 2 plus 16. And we can solve for u. So once I do this, now let's see if we can figure this out. Okay, now just keep in mind order of operations. Okay, this is 16 minus, now 2 to the third is 8, so that's 8u. Okay, now here, folks, I catch a lot of people doing 24 times 2 and then squaring it. Remember, exponent happens before multiplication. So the 2 gets squared, and this result gets multiplied by 24. 2 squared is 4. 4 times 24, 96. 32 times 2 is 64, plus 16. Okay, so let's see what happens here. Okay, so when we do this out, what can we do that cancels out? Anything? Let's see. 96 minus 64, that's 32. Okay, so that's 32. And 32, you got a 16 and a 16. So 32 plus 32 is 64. So what I now have, so 16 plus 96 minus 64 plus 16, it's 16 plus 16 plus 32, 64 minus 8u equals 0. Okay, and that's just kind of combining all my like terms. What I could do now, if I wanted to, is to move the 8u to the other side, add 8u to both sides, divide by 8, and u equals 8. So this only works when u is 8. Um, Now, that's certainly better than the alternative in attempting to do long division. That would be a mess. Because trying to do a long division while trying to keep a u in there and then having to carry a u with you, ew, yuck. That's generally not going to work. So rather than attempting to divide out long division, we can use this property. And that's, again, what this lesson is about, is using this property to kind of avoid having to do the long division every single time we think about factors. Okay, so now let's think about how we could do this in sort of big situation, right? So next question, which of these polynomials could have x minus 2 as a factor? Again, don't do the long division. You could, okay? That would be a colossal, um, I shouldn't say waste, but a colossal ineffective use of your time. When all we have to do is use that fact that we had before. If x minus 2 is a factor, then f of 2 equals 0. And then that means all we have to do is plug 2 into these functions and see if we get a 0 out of it. Okay, now this may require a little bit of calculator use, but we'll try to do our best here, right? Okay, and we'll go through some of these. All right, so we'll just plug 2 in. We don't necessarily have to do all of them, but maybe I'll just pick like the even ones, okay? Or odd ones. Can letters be even and odd? I don't know. We'll try it. Let's just pick 3 of them. Okay, so 6x squared minus 7x minus 5. So again, we're going to plug the 2 in. Remember to do the multiplication last. So this is 24. So 2 squared times 6. So it's 24 minus 7 times 2 is 14, minus 5. Nope, not that one, because that's equal to 5. All right. And let's pick another one. We'll do C and we'll do E as well. Okay, so 2 times 8 is 16. 13 times 4 is 52. 16 times 2 is 32. And 5. Nope, C doesn't work either. Just out of curiosity, does B work? You get 2 squared 2, so that's 12. And 12, 15 times 2 is 30, minus 42. So 42 minus 42 equals 0. B works. Okay. So B totally works. A and C don't. What about one of these longer ones? What about E? Okay. Just trying this out here. So 2 to the 4th is 16. 16 times 8 is 128. Yeah, 16 times 8, because it's going to be 4 plus 8. Yeah, 128. Minus 41 times 8, which is 328, minus 18 times 4 is 72, plus 202, plus 70. I feel like I'm going to need a calculator for that one. Can I pull up a calculator? Let's take a look. Hold on, it's going to load. Maybe, maybe not. Oh, there it is. I see it. Okay. Boop, there we go. Okay, so let's give that a clear and let's try it out. So 128 minus 328 minus 72 plus 202 plus 70. Oh, perfect. It does come out to 0. Okay. And I guess that does make sense. Oh, you know what? I see it here because that's 200. So it's going to be negative 200 plus 202 is going to be 2. And then that's going to be negative 2. So yeah, E totally works. Okay. Okay, so we know that x minus 2 is a factor of that, of those. As an exercise, you can do the other two. Okay, so now let's try something. Let's take the first one, since we already know that x minus 2 is not a factor. Let's go ahead and do the long division on that one. And so let's go ahead and let's do that, right? So if I do 6x squared minus 7x minus 5, and I divide into it x minus 2, let's see what happens. Oops, let's get rid of that. Just make it just look a little bit better. Okay, so 6x squared divided by x, that's 6x minus 12x. Add 1, so change 5x minus 5. So x divided by that's plus 5. And then 5 times that, we get 5x minus 10. And we get a remainder of 5. Not 0. So here's one of the first times that you see a long division that you get a value that's not 0 for a remainder. Now look over here. Didn't we say that when we did the math out, when we plugged 2 in for x, 24 minus 14 is 10, minus 5 is 5. You get a 5 here. Huh. Well, imagine that. So when before we knew that when f of 2 equals 0, that we got a remainder of 0. It turns out you can generalize that to all numbers. Whatever f of, in this case, whatever f of 2 actually equals, the remainder of the division by that factor will give you the same number. Fascinating. So like, for example, this one here, this polynomial here, 16 plus 52 plus 82, that's 84. 84 plus 16 is 100, so this is 105. If we were to do the long division, divide this polynomial by x minus 2, you're going to end up with a remainder of 105 at the bottom. That is what the remainder theorem is. So here's the idea. And so let me state it in a little bit more friendlier terms. Okay. So if we divide, and let's say we have a polynomial, p of x, by x minus a, okay? And so again, it's going to be a factor of this form, x minus a, where then x is the intercept, right? Then the remainder equals p of a, whether it's 0 or not. And so this is incredibly useful when all we care about is whether or not the thing divides, whether you get a 0 or not, or you only really need to know what that remainder is. this becomes useful to avoid long division in those situations. Now, if you still need to know the result of that division, like what happens when you do, like what polynomial you get when you do the division, then yes, you will have to do the long division anyway. So that q of x that you get, right? If you need to know q of x, then yes, you will still have to do the long division. So here's what this is saying, right? And we can actually prove this. So here's another fun thing that I'm actually going to do for you. Again, because you're watching the video, um, I'll go ahead and actually do this. I can actually prove this statement to be true. Okay? And so let's do it on the next page. So what I'm going to do is actually prove the remainder theorem. Okay, now this isn't a proof like geometry. In algebra, we can prove our theorems, but we prove it with algebra, not without, we don't have to use the given and statements and congruence and CPTC and all that other stuff. We don't have to use that here. So instead, let's say we actually try to divide, right? So we're going to take P of X and we're going to actually divide it by X minus A. What would we get? What you're going to get when you divide by X minus A is you're going to get a division result, Q of X. And so Q is going to stand for the quotient, plus you get a remainder term, and we're going to call it R over X minus A. Okay. Now, what I can then do, like this is, again, breaking down the division into a quotient and a remainder. Oftentimes the remainder is 0, but as we discovered in the last one, it doesn't always have to be. Now, you may wonder, why is the remainder written as a fraction? Well, it's the same thing that, like, if you divide, say, let's say you divide 10 by 7. Well, how many times does 10 go into 7, right? Once, with 3 left over. So as a mixed number, 1 and 3/7. And so if a mixed number is a quotient and a remainder. So that's what this is. It's a quotient and a remainder. But now I'm going to multiply both sides by X minus A. And so P of X is equal to Q of X times X minus A plus R. So in other words, what this says here is that P of X is equal to the quotient multiplied by the factor. It's the equivalent of attempting to factor out the X minus A, but that this remainder term that we have to add in order to make, the equation equivalent. So now, what is P of A? P of A is going to be Q of A. Now, we're just going to replace this with A, right? So we're going to replace the X with A. We're going to take that value for the intercept and we're going to plug it in for X. Okay. Now, the first term becomes Q of A. Well, we don't know what that is because that's just the quotient. And that could be like literally anything. But we get A minus A plus R. Well, what's A minus A? 0. And 0 times Q of A is equal to 0. And so P of A is equal to R. So what this is saying is that if I plug that A in for X, I get the same number as what the remainder is. How fancy is that? And there's your proof. There's your first kind of algebra proof. Okay. So that's really kind of what this whole lesson is about. It's just kind of understanding that fact that whether or not you have a factor or whether or not that you don't. And again, it's just really simply a case of, this process can be used to circumvent long division so that you don't have to be busy like spending forever applying long division when we don't have to, when all we care about is whether the remainder exists or not. Okay? Um, so yeah, and this is all based on the fact that you have intercepts and factors that all work together. Okay? All right. Um, all right. I think that's about all that we have here. So we don't need to do much more than that. I hope you have a good night, and I will see you in class whenever.